When I was talking about halohydrin, I talked about anti-addition, and I said, don't you worry about the regiochemistry and the stereochemistry yet, because I'm going to talk about it in a separate video. Here it is. So let me remind you what happens in the halohydrin formation. When we have a halohydrin, the first step is going to be the formation of the bromonium ion. So for example, we will get this bromonium ion right there. Okay, now the second step is going to be the water attacking that bromo ion, the bromonium ion. And the way that can happen, it can be in two different ways. The water could come and attack here, or the water could come and attack here. And as you saw in the previous video, this is a very similar case as the one that we saw of epoxides opening under acidic conditions. What happens when bromonium opens in the presence of water is that it will open, giving us the carbocation that it's more stable. So if we do the same process that we did for the previous video, the one with epoxide openings, we can see that the epoxide could open from this side or could open from that side. If it opens from one side, I will get the Br there. And if it opens from the other side, I will get the Br there. Then the second step will be the water attacking either this position or this position right here. Because this carbocation right there is highly unstable because it's the primary carbocation, these will not form. That product where the OH is all the way at the end is not going to form. However, the Br will end up at the end, and the OH will end up in the more substituted side of the alkene. And so this is something that you have to keep in mind when doing halohydrin formation. So here is again the mechanism. First is the bromonium ion forming, and then the second step is the water coming and attacking. And in this case, the water is going to come and attack from the side that will give us a more substituted carbocation, and then the last step is the deprotonation of that water. And then here, that's how we get the final product where the Br is in the less substituted carbon and the OH is in the more substituted carbon. Here, one more time, the water is going to attack the more substituted carbon, and that's how we get the water connected to that position, the more substituted one. And here, just one more time, on the right side, we have that CH3, which makes that carbon the more substituted one. The reason for that to happen is because this carbocation is stabilized by the alkyl groups. Remember that the more alkyl groups that a carbocation has makes it more stable. What you must recognize is that that type of intermediate is common to three very important reactions that we've seen in this chapter. One of them is the epoxide. The other one is the bromonium ion that I was just talking about. And finally, this mercuridium ion that we saw for the oxymercuration reaction. You see, the three of them are these protonated species, and because the nucleophile in the second step will come and attack from below, that's why we will end up with an anti-type of product. Because if the epoxide is pointing up, or the bromonium or the mercuridium are pointing up, then the nucleophile has to come from below, from the less hindered position. And this is what I've been talking about in this chapter over and over. You must recognize common patterns across different reactions. So you see here, for three reactions that you've seen, the halogenation, the epoxide opening, or the oxymercuration, the intermediates are similar, and because of that, we will get with the anti-type of product because the OH will end up pointing up, and then the nucleophile will be attached here pointing down because this is going to open up. The same is going to happen here, and the same is going to happen on the mercury equivalent.